This is video 4 of chapter 3, and in this video we'll talk about something called the mole. Now this will relate to the atomic mass on the periodic table, so we will show you how we would experimentally use that value. So let's first define the mole. The mole in chemistry is used to count things. It's actually a unit, and just like dozen is a unit to count eggs, we know that a dozen eggs is actually 12 eggs. We can also apply the concept of a dozen to anything else, including atoms. So we can say a dozen atoms is 12 atoms. Similarly, the mole represents a certain number. Now the number is pretty big. In fact, here it is written out. And 6.02 times 10 to the 23. And the reason the number has to be so big is because we are dealing with atoms. Recall that atoms are extremely tiny, so tiny you cannot see them. So you have to have a huge amount to really work with them. And that's why a mole is defined as 6.02 times 10 to the 23 atoms. This number is pretty important. In fact, I would recommend memorizing this number, not only to impress friends, but also to be able to work a bunch of problems, as we'll see. So go ahead, commit this to memory. Let's kind of analyze this number, how big this number is, by a few questions. So here are the questions. Question number 1, if you spent $1 billion, which is a lot of money, there aren't many billionaires in the world, there are a few, but if you spend $1 billion every single second, how long would you need to live to spend a mole, that 6.02 number, times 10 to the 23rd, of dollar bills? Would it be a year? Would it be 10 years? Would it be 50 years, 100, 1,000? No. It would take you 1.9 million years to spend this much money. Huge amount of money. So really tough to visualize it, but that's how many atoms you have, or how big that number is. Question number 2, if you had a mole of marbles, and think of marbles about this size, how much room would they take up? A room, a box, a football stadium, no, no, and no. They would take up the whole entire Earth, and they would stack up 3 miles high around the whole Earth. That is pretty incredible. It shows you how big, again, how huge really this number is. So question number 3, can Mr. Z drink a mole of water molecules? This many water molecules. In fact, I will demonstrate this to you in class, so wait for it. I will, in class, drink a mole of water molecules. And the amount I'll drink is about 1 gulp full. In fact, the amount of water molecules in a mole is about 18 milliliters, which is not much at all. And this tells you how tiny these things are. So we have to have a humongous amount of them to really work with them. So even to have 18 milliliters, you have to have 6.02 times 10 to the 23 of these atoms. So hopefully you gain an appreciation for how big this number is, how important it is as well. And the person that came up with it was Avogadro. This is called Avogadro's number, very famous. And it's given the symbol of N. Big N and little n is given for Avogadro's number. So we can say that 1 mole is this number of atoms, or 1 mole of anything is this number of that anything, but we will relate it to atoms. You're safe to use 3 decimal places here, 6.02 times 10 to the 23rd. What we'll do next is actually we will do some calculations with this number. So let's go ahead and do a few example problems. The first example problem is the following. How many aluminum atoms are there in 2.5 moles of aluminum? So here is aluminum, what our cans are made of. And what we would need to do is do a conversion. Now, we have seen that 1 mole is equal to 6.02 times 10 to the 23rd atoms. This technically is our conversion factor. This is what we will use to convert. So when we convert it, recall, we begin with the number given, in this case 2.5 moles of aluminum, and we will multiply by a conversion factor, and in our conversion factor we will put moles on the bottom because they have to cancel out. Remember, that is the rule. We'll have to put atoms on top, and then our conversion factor is given to us up here, which would mean 1 mole for 6.02 times 10 to the 23rd atoms. Now, you'll have to put this into your calculator, and I will show you how to put this into your calculator. Try it on your own, and see if you come up with this number. Go ahead and try 2.5 times 6.02 times 10 to the 23rd. You should get yourself an answer that looks like this. 1.5 times 10 to the 24th atoms. It should be a big number because we're multiplying by a big number. Now, if you did not get this for the power, then you put the number wrong into the calculator. Go ahead and pause the video, try this on your own, and I will show you, if you're having trouble, how to do this properly in class. In fact, try, after you've done that, go ahead and try this question on your own, which is the same thing. And then let's show you how this number on the periodic table, the atomic mass, is related to the mole. So the number on the periodic table actually gives us two things. Now, the first thing we talked about last time is that it gives you the mass of one atom, one tiny little atom, and that unit is AMU, because we have a special unit for the mass of an atom since atoms are so tiny. However, there is a second thing that that number tells us. And the second thing is it tells you the mass of a mole of atoms. Remember, a mole of atoms is extremely huge. A number is extremely huge. However, this is a perfect amount for us to deal with these elements on our scale. So it also tells you how many grams there are if you have 1 mole of that atom. So if you have a mole of chlorine, it will weigh 35.45 grams. And this is the beauty. The mole allows us to connect ourselves to the atom through this number, 35.45. And let's show you how we're going to use that. So the question here is convert 25.5 grams of carbon to moles of carbon. Carbon comes in two varieties. This is coal and this is diamond. Carbon is actually both of these. So let's convert just like we've done previously. Let's begin with what we're given. In this case, 25.5 grams of carbon. I'll go ahead and symbolize carbon with just a C. Then we have to multiply it by our conversion factor. According to the rules, grams of carbon will go on the bottom, and moles of carbon will go on top. That is what we're asked for, moles of carbon. Now, the relationship here will come from the periodic table. And if you take a look at carbon on the periodic table, carbon will have 12.01 on the bottom of it and a 6 on top. So this is now the mass that we're going to use. This is the mass in 1 mole of carbon. So a mole of carbon has 12.01 grams of carbon. And this is how you would use the mass from the periodic table in calculations. In fact, this is the most common way that we will be using this mass. So if you put this in your calculator, go ahead and do it. You should get yourself 2.12 moles of carbon. Go ahead and put carbon at the back. So this is how we will use the periodic table number for our calculations. Let's go ahead and do the same thing, or in fact, go ahead and try the same thing on your own. Pause the video and try this on your own. This next slide summarizes what we've just done. We've done two types of problems, both of them involving the mole. And what we first said is that a mole is equal to this many atoms. Now this is true for any element. What we mean is it doesn't matter which element you're dealing with, a mole of it will be this many atoms. However, the mass that we took from the periodic table is specific for every element. So for carbon, a mole of carbon weighs 12.01 grams. A mole of chlorine weighs 35.45 grams. And a mole of iron will be 52 grams, 56 grams, and so forth. So it is different for every element. So the way to think about this big conversion factor relating to the mole. The mole gives us two things. It tells us how many atoms you have and how many grams you have. So what you can do is you can actually convert from grams of a substance all the way to atoms of the substance, but you'll have to go through moles. And what we say is that moles are in the middle. Likewise, if you want to convert from atoms to grams of a substance, you'll have to go through moles. So this will be a two-step conversion. In fact, let's go ahead and try this. Let's do this for our end here. Example 10, which asks how many atoms are there in 1.5 grams of iron. This will be a two-step conversion, and we will be going through the concept of the mole. So as usual, we'll begin with 1.1 grams of iron. Iron's symbol is Fe. And in this case, because it's a two-step, let's go ahead and set up two conversion factors. What we'll do is we'll go through moles. So because moles are in the middle, we'll first go from grams of Fe to moles of Fe, and then we'll go from moles to atoms. So take a look, pause and take a look at this little problem, and now we can fill in the mass. Now remember, the mass that relates the moles to grams comes from the periodic table. So if you take a look at iron, find iron, and the mass should be 5585. Make sure it's right. So remember, this tells you how many grams there are in a mole. So a mole is 55.85 grams. Now for mole to atoms, this number never changes, no matter which element you're dealing with. And a mole, recall, is 6.02 times 10 to the 23rd atoms. So in this case, you have to multiply by two conversion factors. Go ahead and try this on your own. Take a minute and try this. Do 1.1 times 1 divided by 5585 times 6.02 times 10 to the 23rd. Divide by 1, and you should get yourself 1.2 times 10 to the 22nd atoms. What this means, if you have 1.1 grams of iron and a paperclip contains 1.1 grams of iron, you can calculate how many atoms there are in this paperclip. And this is pretty fascinating. You can give a friend a paperclip and tell the friend, I will tell you how many atoms there are in this paperclip. And to the amusement and amazement of your friends, you proceed to show them the calculation, and you have counted how many atoms there are in this paperclip, because the paperclip is made of iron. And this is the power of the mole. So go ahead and try this problem on your own, and we will do this once again a few more times in class. Thanks for watching.